In 2007, a group of scientists working with the National Research Council got together to think about something strange. The committee was led by a man named John A. Barros. Their job was to write a report, not about life as we know it, but about life as we don't. They called it Weird Life, the final report, titled "The Limits of Organic Life in Planetary Systems," looked at possibilities that sound like fiction. They seriously considered whether life could exist without water. They wondered if silicon could replace carbon as the backbone of biology. One place they focused on was Titan, Saturn's largest moon. Titan is brutally cold, around minus 179 degrees Celsius. It has lakes, rivers, and rain. But this weather system is not made of water. It is made of liquid methane and ethane. The committee asked a simple, profound question. Could something be swimming in those methane lakes? Could a form of life exist there, breathing hydrogen instead of oxygen, with a body built from chemicals we'd consider poison? This wasn't just a thought experiment. It was a formal scientific exploration into how vast the definition of life might be. It was a small official acknowledgement that the universe might not just be bigger than we think, but weirder than we can possibly think. And this is where the human mind starts to hit a wall. We are built to understand our local environment. We understand rocks, trees, and water. But the cosmos operates on a scale of size, time, and strangeness that our brains did not evolve to handle. Infinity is not just a big number, it is a completely different concept, and it is everywhere we look in the universe. Number 24, the universe might be a mathematical object. The physicist Eugene Wigner wrote a paper in 1960 called "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He was puzzled by something. Why is it that abstract mathematical concepts, often invented by mathematicians with no thought for the real world, turn out to describe the universe with perfect accuracy? Einstein's general relativity, which describes gravity, is based on complex differential geometry developed decades earlier. The quantum world runs on abstract matrix algebra. It seems like a bizarre coincidence. It's as if someone wrote a user manual for the universe using a language we just happened to stumble upon. The physicist Max Tegmark at MIT proposed a radical answer to this. His idea is called the mathematical universe hypothesis. The hypothesis is not that the universe is just described by math. The hypothesis is that the universe is a mathematical structure. This is a difficult idea. We think of math as a tool we use, but in this view, everything around you, from the chair you're sitting on to the thoughts in your head, is part of a giant, complex mathematical object. You are not a body of atoms that follows mathematical laws. You are a self-aware part of the mathematical structure itself. A simple analogy is a computer game. A character in the game might perceive a world of mountains and skies. But from the outside, we know it is all just code. It is information being processed. The character is not described by the code. The character is the code. Tegmark suggests our physical reality is the same. There is no difference between the mathematical equations and the universe they represent. They are the same thing. This idea has huge implications. If our universe is just one possible mathematical structure, then every other consistent mathematical structure must also exist as its own separate universe. This means there would be an infinite number of other universes, some slightly different from ours, and others based on mathematics so bizarre we cannot even conceive of them. It suggests that our universe is not special, it is just one entry in an infinite library of all possible mathematical forms. The reason our universe seems so perfectly tuned for life is simply that we are self-aware substructures. We can only exist in a mathematical structure complex enough to support self-aware substructures. There is no luck involved. The main problem with this idea is that it might be impossible to prove or disprove. How could we, from inside our mathematical structure, ever get evidence of another one? It remains a philosophical, almost spiritual idea born from the strange fact that the cosmos seems to obey a language of pure logic. Number 23, your brain might be a random fluctuation in the void. The second law of thermodynamics is one of the most fundamental rules of the universe. It states that entropy, or disorder, always tends to increase. A hot cup of coffee will always cool down to match the room's temperature. A neat room will get messy over time. The universe itself is heading towards a state of maximum disorder known as heat death, where everything is a uniform, lukewarm soup of particles. But this is a statistical law, not an absolute one. Over very, very long timescales, random fluctuations can happen. It is technically possible, though fantastically improbable, for all the air molecules in your room to suddenly rush into one corner. It is also possible for particles in the cold, empty void of the far future to randomly bump into each other and assemble something complex. The physicist Ludwig Boltzmann considered this in the 19th century. This leads to a disturbing thought experiment called the Boltzmann brain. Given an infinite amount of time, which the universe might have, absolutely every possible arrangement of particles will eventually happen. This includes the spontaneous formation of a fully functioning human brain, complete with a lifetime of memories, floating in the emptiness of space. This is not just a possibility in some cosmological models, it is a statistical certainty. In fact, over infinite time, it is far more likely for a single conscious brain to pop into existence out of chaos than it is for an entire complex, low-entropy universe like ours to be born from a Big Bang. The universe we see, with its billions of galaxies and consistent physical laws, is an incredibly ordered system. A single brain is a much smaller, and therefore statistically more probable fluctuation. This leads to a terrifying conclusion. If this is true, how do you know you are not a Boltzmann brain? You have memories of growing up, of eating breakfast this morning, of reading these words. But for a Boltzmann brain, all of those memories would have just popped into existence along with the brain's physical structure a moment ago. There would be no way to tell the difference from the inside. You would feel completely real, but you would just be a temporary island of order in an ocean of chaos, destined to dissolve back into randomness in the next instant. Most physicists use this as a paradox to show that something is wrong with our current models of the cosmos. If a theory predicts that we are overwhelmingly likely to be Boltzmann brains, then that theory is probably wrong, because it cannot be trusted. After all, the very laws of physics we use to deduce the theory would just be part of the random memories of the Boltzmann brain. It is a perfect loop of cosmic doubt. Number 22, time might not be passing at all. Our entire experience is built on the idea of time flowing. The past is gone, the future is yet to come, and we live in the fleeting moment of the present. This feels like the most obvious truth in the world, but in physics, this idea is almost completely absent. In Einstein's theory of relativity, time is just another dimension, like length, width, and height. It is woven together with space into a single four-dimensional fabric called spacetime. The theory describes the entire history of the universe as a complete, unchanging, four-dimensional block. This is often called the block universe model. In this view, the past, present, and future all exist simultaneously. The dinosaurs are not gone, your future grandchildren are not yet to be born, they all exist in their own coordinates in the block of spacetime, just as the city of Paris exists at its own coordinates on the globe of the Earth. The feeling that time is passing is just a trick of human consciousness. A physicist named Julian Barbour is a leading proponent of this idea. He argues that there is no time at all. There is only a series of nows. The universe is an infinite collection of these individual moments, like still frames of a movie film. The sense of flow and movement comes from our minds processing these frames in a particular order, creating a story with a past and a future. Our memories are just neurological patterns that exist in the current now, which we interpret as being from a previous now. Why does it seem to move in one direction? This is tied to entropy. The nows our consciousness connects are ordered in a way that shows increasing complexity and disorder. We mistake this sequence of increasing entropy for the arrow of time. So when you remember breaking a glass, you are not remembering a past event. You are experiencing a brain state in the present that contains the information of a less ordered arrangement of glass particles. The universe itself does not move through time. It just is. All of it. All at once. This completely changes our understanding of existence. It means that moments of great joy are not lost forever in the past. They are permanently part of the fabric of reality, but it also means that moments of great suffering are equally permanent. Nothing ever truly goes away. It is all just there, frozen in the block of space-time. Number 21. There could be an infinite ladder of higher dimensions. We live in a world of 3 spatial dimensions, up, down, left, right, forward, backward. We can barely picture a 4th spatial dimension. The typical analogy is a 2D flatlander trying to comprehend a 3D sphere passing through their flat plane. They would only see a circle that grows and then shrinks. They could never see the whole sphere at once. Our perception of a 4D object or hyperobject would be similarly limited. But some of the most advanced theories in physics require more than just 3 spatial dimensions to work. String theory, for example, is a candidate for a theory of everything that unites quantum mechanics and general relativity. For its mathematics to be consistent, it requires the universe to have at least 10 spatial dimensions. So where are these other dimensions? The common explanation is that they are compactified. They are curled up on themselves at an incredibly tiny scale, the Planck length, which is trillions of times smaller than an atom. Think of a garden hose. From far away, it looks like a 1D line. But if you get very close, you see it has a second dimension, the circular circumference. The extra dimensions of string theory are thought to be curled up like this everywhere in space, too small for us to ever notice or access directly. But M theory, an extension of string theory, goes even further. It suggests 11 dimensions. In this view, our entire 4-dimensional universe 3 space one time might be a brane, short for membrane, floating in a higher dimensional space called the bulk. There could be other branes, other universes, floating parallel to ours in this bulk. This opens up some wild possibilities. Gravity, which is much weaker than the other fundamental forces, might be the only force that can leak between these branes. This could explain why it is so weak in our universe. It could also mean that events in another universe, in another dimension, could have a gravitational effect on ours. This is one of the proposed explanations for dark matter. It might be normal matter in a parallel brane right next to ours, which we can feel the gravity of, but can never see or touch. This isn't just a mental exercise. The Large Hadron Collider has been used to look for evidence of extra dimensions. The idea was that if 2 particles were smashed together with enough energy, some of that energy could be ejected into another dimension, appearing to us as missing energy in the final calculation. So far, no such evidence has been found, but the possibility remains that we are living on a thin slice of a much larger, infinitely more complex reality. Number 20, the universe had no beginning. We are told that the universe began with the Big Bang about 13.8 billion years ago. The common picture is a single, infinitely dense point, a singularity that exploded and created space, time, and everything we see. But this idea of a beginning from nothing is a major problem in physics. The laws of physics, as we know them, break down at a singularity. It is a point where the math gives us infinite answers, which means it is not giving us an answer at all. So some physicists have started to explore models where the Big Bang was not a beginning, but a transition. One such idea is the Big Bounce. This model suggests that our universe is part of an infinite cycle of expansion and contraction. The universe we are in now is expanding, but eventually gravity might pull everything back together. It will collapse in on itself in a big crunch. But instead of collapsing into a singularity, quantum effects would take over at a very high density and cause the universe to bounce back, triggering a new Big Bang and a new phase of expansion. In this model, our universe was born from the ashes of a previous one, and it will one day give birth to a future one. The cycles could go on forever, into the infinite past and the infinite future. There was no first moment. There will be no last. Another model is conformal cyclic cosmology proposed by the physicist Roger Penrose. In this view, the universe expands forever until it reaches a state of heat death, where it is composed only of massless particles like photons. At this point, the universe loses its sense of scale. Without mass, there is no way to measure size or time. The infinitely large, cold future of one universe becomes mathematically identical to the infinitely small, hot, dense state of a Big Bang. The end of one aeon becomes the beginning of the next. The cosmic microwave background radiation, the leftover heat from our Big Bang, might even contain faint traces or Hawking points from the black holes that evaporated at the end of the previous aeon. In Penrose and his team have even claimed to have found some tentative evidence for these points, though the claim is highly controversial in the physics community. These theories get rid of the troubling idea of a singularity and the philosophical problem of creation from nothing, or they replace it with an even more mind-bending concept, a universe that is truly eternal, with no beginning and no end. Number 19, the emptiest space is a hissing foam of infinite energy. We think of empty space, a vacuum, as nothing. The void between planets and stars is the definition of emptiness. But according to quantum mechanics, this is completely wrong. A perfect vacuum, completely devoid of all matter and energy, is impossible. Even the emptiest space in the universe is seething with activity. This is due to the Heisenberg uncertainty principle. This principle states that you can never know certain pairs of properties of a particle, like its position and momentum, with perfect accuracy at the same time. A similar uncertainty exists for energy and time. This means that for very short periods of time, energy can be borrowed from the vacuum to create pairs of particles and antiparticles. These are called virtual particles. They pop into existence, exist for a fraction of a second, and then annihilate each other, paying back the energy loan. This process is happening constantly, everywhere, at every point in space. The emptiest vacuum is actually a bubbling, chaotic foam of these virtual particles appearing and disappearing. This is not just a theory, it has measurable effects. One is the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, they will be pushed together. The reason is that only virtual particles of certain wavelengths can fit between the plates, while virtual particles of all wavelengths can exist outside the plates. This creates a pressure difference, with more pressure on the outside pushing the plates in. This effect was predicted in 1948 by Hendrik Casimir, and has been experimentally verified numerous times. It is physical proof that the vacuum is not empty. The energy of this vacuum, called zero-point energy, is theoretically enormous. If you add up all the potential energy from these quantum fluctuations at every point in space, you get an infinite number. Physicists have to use a mathematical trick called renormalization to get rid of this infinity and make their calculations work. But some models suggest that even after this, the remaining vacuum energy should be huge. It should be so large that its gravitational effect would have ripped the universe apart instantly. This is known as the cosmological constant problem, and it is one of the biggest unsolved mysteries in physics. The measured value of the cosmological constant, which is driving the accelerated expansion of the universe, is about 120 orders of magnitude smaller than the theoretical prediction. It is the most wrong prediction in the history of science. It tells us that our understanding of the most fundamental aspect of reality, the nature of nothing, is profoundly, infinitely wrong. Number 18, an infinite amount of information can fit inside a black hole. A black hole is often described as a point of infinite density, a singularity wrapped in an event horizon. Nothing, not even light, can escape once it crosses the event horizon. For a long time, it was thought that anything that fell into a black hole was lost forever. Its information, the unique arrangement of its atoms, was simply erased from the universe. This created a huge problem. A fundamental law of quantum mechanics is that information can never be destroyed. It can be scrambled, but it must always be preserved. The idea that black holes destroyed information led to the black hole information paradox, a deep conflict between general relativity and quantum mechanics. In the 1970s, Stephen Hawking showed that black holes are not completely black. Due to quantum effects near the event horizon, they slowly emit radiation, now called Hawking radiation. This means that black holes can evaporate and shrink over incredibly long timescales. A solar mass black hole would take about 10 raised to the power of 67 years to evaporate, vastly longer than the current age of the universe. But if the black hole eventually disappears completely, what happens to the information of all the things that fell into it? This deepened the paradox. A solution came from an unexpected direction, from a concept called the holographic principle. It was proposed by Gerard 't Hooft and later developed by Leonard Susskind. The idea is that all the information about a volume of space can be encoded on its boundary, like a two-dimensional hologram projecting a three-dimensional image. When something falls into a black hole, its information is not lost, it gets stuck and scrambled on the surface of the event horizon. As the black hole evaporates via Hawking radiation, that information is slowly and subtly encoded into the outgoing radiation and returned to the universe. The amount of information a black hole can store is proportional to its surface area, not its volume. The surface area of the event horizon is measured in units of Planck area, the smallest possible unit of area. Each tiny Planck area can store one "it" of information. The Bekenstein-Hawking entropy formula quantifies this. The entropy, which is a measure of information of a black hole, is enormous. A black hole with the mass of the sun has an event horizon with a radius of about 3 kilometers. The amount of information it can store is about 10 raised to the power of 77 bits. This is more information than is contained in all the normal matter in the entire observable universe. It suggests that the ultimate storage capacity of the universe is not in its volume, but on its surfaces. Number 17, the universe is fine, tuned on an infinitely sharp knife edge. The universe we live in seems to be incredibly fine-tuned for the existence of life. There are a number of fundamental physical constants like the strength of gravity, the charge of an electron, and the mass of a proton. If any of these constants were changed by even a tiny, tiny fraction, the universe would be completely different and almost certainly lifeless. For example, the strong nuclear force binds protons and neutrons together in an atom's nucleus. If it were just 2% stronger, all the hydrogen in the early universe would have fused into heavier elements. There would be no hydrogen to form water, the basis of life as we know it. Stars like our sun would not exist. If it were 5% weaker, protons and neutrons would not be able to bind together at all. No atoms other than hydrogen could form. There would be no chemistry, no planets, and no life. Another example is the cosmological constant, the energy of empty space that is causing the universe's expansion to accelerate. Its measured value is incredibly small. If it were much larger, its repulsive force would have ripped the nascent universe apart before any galaxies or stars could form. If it were negative and large, the universe would have collapsed back in on itself moments after the Big Bang. The physicist Martin Rees described 6 numbers that, if they were not set to their precise values, would make our universe uninhabitable. The level of precision required is staggering. For the cosmological constant, it is like taking a pencil and trying to balance it on its tip for 13.8 billion years. It is like firing a rifle at a 1-inch target a billion light years away and hitting it bullseye. Why is the universe like this? There are three main explanations. The first is pure luck. We just happen to win an infinite cosmic lottery. The odds are so small that most scientists find this unsatisfying. The second is a designer. Some believe this precision points to a creator who intentionally set the dials to the right values to allow for life. This is a philosophical or religious argument, not a scientific one, as it cannot be tested. The third, and the one favored by many physicists, is the multiverse. If there's an infinite number of universes, each with its own randomly set physical constants, then it is no surprise that we find ourselves in one of the very few that can support life. We could not exist to observe the others. This is called the anthropic principle. We see the universe as fine-tuned for the same reason a fish sees its pond as perfectly suited for fish. It is a selection effect. We won the cosmic lottery because there are an infinite number of tickets. Number 16, the future might last for an infinitely long time. We measure the age of the universe as 13.8 billion years. This seems like a long time. But when we look at the potential future of the cosmos, it is barely the first tick of the clock. If our current understanding of cosmology is correct, the universe is destined for a future of near infinite duration. This future is often described in eras. We are currently in the Stellarius era, the age of stars. Stars are being born, they shine, and they die. This era will last for about 100 trillion years, 10 raised to the power of 14 years. This is almost 10,000 times longer than the universe has existed so far. By the end of this era, the last red dwarf stars, the longest-lived stars, will have burned out. The universe will go dark. Then comes the degenerate era. The only objects left will be the remnants of stars, white dwarfs, neutron stars, and black holes. The galaxies will have dissolved, their dead stars drifting through an expanding, cold darkness. This era will be unimaginably long. Over timescales of 10 raised to the power of 37 years, protons themselves might decay, causing the dead stars and planets to slowly dissolve into radiation and subatomic particles. After the last proton decays, the only large objects left will be black holes. This begins the black hole era. The black holes will be the last organized structures in the universe, but they too will eventually die. Through Hawking radiation, they will slowly evaporate. The smallest black holes will go first. The supermassive black holes at the centers of what used to be galaxies will be the last to go. A supermassive black hole could take 10 raised to the power of 100 years to evaporate completely. This number is so large, it is called a googol. Writing it out would require a 1 followed by 100 zeros. The entire age of the universe so far is a number with only 10 zeros. Finally, after the last black hole has evaporated into a final puff of low-energy photons, the universe enters the dark era. It will be a near-perfect vacuum, a thin, cold soup of photons, neutrinos, and a few stray electrons and positrons, all drifting ever further apart as the universe continues to expand. In this state, very little will ever happen again. Time will lose its meaning. This heat death of the universe could last for an eternity. It is a future of almost infinite time, but almost zero events. It challenges our very notion of what it means to exist. Number 15, an infinite number of you are reading this right now. Quantum mechanics is the science of the very small. It has a reputation for being weird, and one of its weirdest aspects is superposition. A subatomic particle, like an electron, can exist in multiple states at once until it is measured. It can be spinning both clockwise and counterclockwise at the same time. It can be in multiple locations at once. When we measure it, the particle seems to choose one state. This is called the collapse of the wave function. But what does that actually mean? In the 1950s, a graduate student at Princeton named Hugh Everett III came up with a radical interpretation. He proposed that the wave function never collapses. When you make a measurement, the universe itself splits into multiple branches. In one branch of the universe, the electron is spinning clockwise. In another, identical branch, it is spinning counterclockwise. Both outcomes happen. They just happen in separate parallel universes. This is the many worlds interpretation of quantum mechanics. Every time a quantum event has more than one possible outcome, the universe splits. This is happening constantly, trillions of times a second, all over the universe. The number of parallel universes is staggeringly large, possibly infinite. This means there are an infinite number of alternate realities. In one universe, the asteroid that killed the dinosaurs missed the Earth. In another, you chose a different career. In yet another, you wore a different shirt this morning, and somewhere in this infinite multiverse, there is a universe that is exactly identical to this one in every single way, except for the position of one single atom on the far side of the Andromeda Galaxy. More than that, if the number of universes is truly infinite, then every single thing that is not forbidden by the laws of physics must happen somewhere. There is a universe where you are a celebrated astronaut. There is one where you are living on Mars. And there are an infinite number of universes where a person who is physically identical to you, with all your memories and thoughts, is sitting and reading this exact sentence at this exact moment. This idea is not science fiction. It is a serious, though controversial, solution to the measurement problem in quantum physics, supported by physicists like Sean Carroll and David Deutsch. It avoids the strange idea of a conscious observer being needed to collapse the wave function. The universe just carries on, branching into every possibility with no need for an observer. The different versions of you in these other universes are not in the sense that you can communicate with them. Each branch is its own separate reality, but they all share a common past, up until the point where they split. Number 14 space might be infinitely divisible, or it might not be. We can take a ruler and measure a meter, we can measure a centimeter, we can measure a millimeter. Is there a limit to how small we can go? Can we keep dividing a length of space in half forever? The Greek philosopher Zeno wrestled with this in his famous paradoxes. To cross a room, you must first cross half the room. Then you must cross half of the remaining distance, and so on. You would have to complete an infinite number of smaller and smaller tasks, which seems impossible. Yet, we cross rooms all the time. For most of history, space and time were thought to be continuous and infinitely divisible. But modern physics suggests there might be a fundamental limit. There might be a pixel of space-time, a smallest possible unit of length and time that cannot be divided any further. This smallest possible length is called the Planck length. It is about 1.6 × 10 raised to the power of 35 meters. This is incredibly small. If you were to scale up an atom to be the size of the observable universe, the Planck length would be about the height of a tree. The shortest possible unit of time is the Planck time, which is the time it takes for light to travel one Planck length. It is about 10 raised to the power of 43 seconds. Below these scales, our current laws of physics, both general relativity and quantum mechanics, break down completely. Space and time, as we know them, cease to have meaning. At this Planck scale, space is thought to be a chaotic, bubbling quantum foam. Tiny black holes and wormholes might be constantly popping in and out of existence. The geometry of space-time would be incredibly distorted and turbulent. So, which is it? Is space a smooth, continuous fabric that can be divided forever? Or is it a pixelated, grainy grid made of indivisible units? This is one of the biggest open questions in physics. A theory called loop quantum gravity, a competitor to string theory, suggests that space is indeed quantized. It proposes that the fabric of space-time is woven from tiny, discrete loops. If this is true, it would solve many of the infinity problems that plague physics. But we currently have no way to test it. Probing the Planck scale would require a particle accelerator the size of our galaxy. So for now, we are left with two equally mind-bending possibilities. Either space goes on forever into the infinitely small, or there is a hard, fundamental wall at the bottom of reality. Number 13, most of the universe is made of something we can't see. Look around you. Everything you see, the Earth, the sun, the stars, is made of normal matter. Atoms, protons, neutrons, electrons. For a long time, we assumed that the entire universe was made of this stuff. We were wrong. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster of galaxies. He noticed something strange. The galaxies in the cluster were moving so fast that they should have flown apart. The gravity from all the visible stars and gas was not nearly enough to hold the cluster together. He proposed that there must be some kind of invisible matter, which he called Dunkelmaterie, or dark matter, providing the extra gravitational pull. His idea was ignored for decades. Then, in the 1970s, the astronomer Vera Rubin was studying the rotation of individual galaxies. She found that the stars on the outer edges of galaxies were moving just as fast as the stars near the center. This defied Newton's laws of gravity. It was like seeing the outer planets of our solar system orbiting the sun as fast as Mercury. The only way to explain this was if the galaxies were embedded in a massive, invisible halo of dark matter, with its gravity holding the fast-moving stars in their orbits. Today, the evidence for dark matter is overwhelming. We see its gravitational effects everywhere, from the bending of light from distant galaxies, gravitational lensing, to the large-scale structure of the cosmic web. And it is not just a small component. Our best measurements from missions like the Planck satellite tell us that normal matter, the stuff we are made of, makes up only about 5% of the total mass and energy content of the universe. About 27% is dark matter. The remaining 68% is even more mysterious dark energy. This was discovered in 1998 when two teams of astronomers found that the expansion of the universe is not slowing down, as everyone expected, but speeding up. There is some kind of energy inherent in space itself, a sort of anti-gravity that is pushing everything apart at an ever-increasing rate. We have no idea what dark matter or dark energy are. Dark matter does not emit, absorb, or reflect any light, so we cannot see it. We only know it is there because of its gravity. The leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles, or axions, but decades of searching with sensitive detectors deep underground have found nothing. Dark energy is an even bigger mystery. It seems to be a property of the vacuum of space itself, but its measured strength is bizarrely small compared to theoretical predictions. It means that 95% of the cosmos is an infinite mystery. We live in a universe whose fundamental composition is completely unknown to us. Number 12, the cosmos is not expanding into anything. The universe is expanding. We have known this since Edwin Hubble's observations in the 1920s. We see distant galaxies moving away from us, and the farther away they are, the faster they are moving. This leads to a common question. What is the universe expanding into? It is a natural question, but it is based on a wrong mental picture. We think of the Big Bang as an explosion in a pre-existing empty space, but that is not what happened. The Big Bang was not an explosion in space, it was the explosion of space. Space itself was created in the Big Bang and has been stretching ever since. An analogy is to think of the surface of a balloon. Draw some dots on the balloon to represent galaxies. As you inflate the balloon, the surface area stretches. Every dot moves away from every other dot. An observer on any dot would see all the other dots rushing away from them, but the dots are not moving across the surface. The surface itself is expanding. The balloon is not expanding into anything. It is just getting bigger. Our three-dimensional universe is like the two-dimensional surface of that balloon. The expansion is happening everywhere at once. It is an intrinsic stretching of the fabric of space-time. This is why there is no center of the universe. The Big Bang did not happen at a particular point in space. It happened everywhere. Every point in our current universe was at the location of the Big Bang 13.8 billion years ago. This also helps to understand the observable universe. We can only see out to a distance of about 46.5 billion light years. This is not because there is an edge or a wall there. It is because the universe is only 13.8 billion years old. The light from galaxies beyond that cosmic horizon has not had enough time to reach us yet, and because space is expanding faster than the speed of light at those distances, it never will. The universe beyond our horizon could be vastly larger, perhaps even infinite. We are just on a small island of visibility in a potentially infinite stretching sea of space-time. Number 11, the universe could be a sphere that repeats itself. What is the overall shape of the universe? This is a fundamental question in cosmology. According to Einstein's theory of general relativity, space-time can be curved by mass and energy. On a cosmic scale, there are three main possibilities for the geometry of the universe. It could be flat, like a sheet of paper. In a flat universe, parallel lines will always stay parallel, and the angles of a triangle add up to 180 degrees. This is the geometry we learn in school. It could be open or negatively curved like the surface of a saddle. In an open universe, parallel lines will eventually curve away from each other, and the angles of a triangle add up to less than 180 degrees. Both flat and open universes are infinite in extent. The third possibility is that the universe is closed or positively curved like the surface of a sphere. In a closed universe, parallel lines will eventually meet, and the angles of a triangle add up to more than 180 degrees. A closed universe is finite in size, but it has no edge. Just like on the surface of the Earth, if you travel in a straight line for long enough, you will eventually end up back where you started. Current measurements from the cosmic microwave background suggest that the universe is very, very close to flat. But there is a margin of error. It is still possible that the universe has a slight positive curvature. If the universe is a finite, closed sphere, it could have a strange topology. It could be a hypersphere, the 3D equivalent of a 2D sphere's surface. But it could also be something more complex, like a 3 torus, which is shaped like a giant 3-dimensional donut. If we lived in a donut-shaped universe and we looked far enough in one direction, we would eventually see the back of our own head. The light would have traveled all the way around the universe and come back to us. We would see copies of our own galaxy and every other galaxy repeated over and over again in the sky. Astronomers have searched for this. They have looked for repeating patterns or circles in the cosmic microwave background that would be a sign of a finite, repeating universe. So far, they have found no conclusive evidence. The data suggests that if the universe is finite and repeating, it must be larger than the part we can observe. The idea is tantalizing. Our vast cosmos might just be one cell in an infinite cosmic wallpaper, a single pattern that tiles the fabric of reality forever. Number 10, the speed of light is a cosmic speed limit, but space itself can break it. The speed of light in a vacuum, about 300,000 kilometers per second, is famous as the ultimate speed limit of the universe. According to Einstein's special theory of relativity, nothing with mass can ever reach the speed of light, and nothing, not even information, can travel through space faster than light. This seems straightforward, but it comes with a major exception. The speed limit applies to motion through space. It does not apply to the expansion of space itself. The fabric of space-time can and does expand faster than the speed of light. This is not a violation of relativity. Nothing is traveling through space to break the speed limit. Rather, the space between objects is being created. Think of a long rubber band with ants on it. The ants can only crawl at a certain maximum speed along the rubber band. This is their speed limit. But if you stretch the rubber band very quickly, 2 ants that are far apart can be moving away from each other at a speed much greater than their crawling speed. Neither ant is breaking its own speed limit. The space between them is just expanding. This is what is happening in our universe. For galaxies that are relatively close to us, like Andromeda, their motion away from us is slow. But for very distant galaxies, the amount of space between them and us is huge, and every bit of that space is expanding. The cumulative effect is that these distant galaxies are receding from us at speeds faster than the speed of light. This is why the observable universe has a horizon. Any galaxy beyond a certain distance, currently about 14.5 billion light years away, is receding from us faster than light. The light that those galaxies emit today can never reach us. The space between us and them is stretching too fast for the light to overcome it. We are seeing these galaxies as they were in the distant past when they were closer to us. But we will never see what they look like, no. This also has implications for the far future. As the accelerated expansion driven by dark energy continues, more and more galaxies will be pushed beyond our cosmic horizon. They will cross the point where their recession speed exceeds the speed of light. Their light will be redshifted into oblivion, and they will disappear from our sky one by one. Eventually, billions of years from now, our local group of galaxies will be the only thing visible. The night sky will be dark and empty. We will be an isolated island in an expanding, invisible, and infinitely lonely cosmos. Number 9. There might be white holes, the opposite of black holes. General relativity is the theory that describes gravity as the curvature of spacetime. The equations of general relativity are very complex, and they often have strange solutions. One of the most famous solutions describes black holes, regions of spacetime where gravity is so strong that nothing can escape. The equations for a black hole were derived by Carl Schwarzschild in 1916, but the mathematics of these equations is time symmetric. This means that if you have a valid solution, you can run the clock backwards and get another valid solution. If you take the Schwarzschild solution for a black hole and run it backwards in time, you get a white hole. A white hole is the exact opposite of a black hole. It is a region of spacetime from which things can escape, but into which nothing can ever enter. Like a black hole, it has a singularity and an event horizon, but matter and energy can only ever travel outwards from a white hole. It is like a cosmic fountain spewing out matter and energy. While black holes are predicted by the theory and we have overwhelming observational evidence for their existence, white holes are purely hypothetical. We have never seen one. Most physicists believe they probably do not exist in nature. The problem is that they seem to require a very special, unlikely set of starting conditions. To form a black hole, you just need to collapse a massive star. To form a white hole, you would need a singularity to have existed since the beginning of the universe, with no collapsing matter to form it. They are also thought to be incredibly unstable. Any tiny amount of matter falling towards a white hole would be blue shifted to have an infinite amount of energy at the event horizon, which would likely cause the white hole to collapse into a black hole immediately. However, some physicists have speculated about their possible role in the cosmos. One idea is that the Big Bang itself might have been a white hole, a single universe-sized white hole from which all the matter and energy of our cosmos erupted. Another more speculative idea from the field of loop quantum gravity is that black holes and white holes could be connected. When a massive star collapses to form a black hole, it might not form a true singularity. Instead, quantum gravity effects could cause it to bounce and emerge as a white hole somewhere else in spacetime or even in another universe. In this view, a black hole is a cosmic doorway and a white hole is the exit. Number 8. The Fermi paradox means the silence of the universe is terrifying. Our galaxy, the Milky Way, contains an estimated 200 to 400 billion stars. The observable universe contains an estimated 2 trillion galaxies. Many of these stars have planets. A significant fraction of those planets are likely to be in the habitable zone where liquid water could exist. Given these numbers, the universe should be teeming with life, including intelligent, spacefaring civilization. The galaxy should be noisy with radio signals and filled with alien probes. So, as the physicist Enrico Fermi famously asked his colleagues during a lunch in 1950, "Where is everybody?" This is the Fermi paradox. It is the stark contradiction between the high probability of extraterrestrial life and the complete lack of any evidence for it. There are many proposed solutions to this paradox, and most of them are unsettling. One possibility is that intelligent life is incredibly rare. The sequence of events that led to humanity, from the formation of a stable planet to the evolution of consciousness, might be a fluke of such colossal improbability that it has only happened once in our galaxy, or even in the entire observable universe. This is the rare Earth hypothesis. Another possibility is that intelligent civilizations inevitably destroy themselves before they can become interstellar. They might succumb to nuclear war, climate change, or an out-of-control artificial intelligence. In this view, there is a great filter ahead of us, a hurdle that is almost impossible for any species to overcome. We may be approaching it ourselves. A more recent and darker solution is the dark forest hypothesis, popularized by the science fiction author Liu Cixin. In this scenario, the universe is full of intelligent life, but it is a dangerous place. Any civilization that reveals its existence to the cosmos is taking a huge risk. It is impossible to know the intentions of another alien civilization. They could be peaceful or they could be hostile predators. Since the stakes are existential, the only safe strategy is to remain silent and hidden. And if you do detect another civilization, the safest move is to eliminate it before it can eliminate you. The universe is a dark forest, and every civilization is a hunter with a gun, hiding behind a tree. The silence we observe in the sky is not because the forest is empty. It is because no one dares to make a sound. The first one to shout, "I'm here," is the first one to get shot. This would mean that our own radio broadcasts, which have been leaking out into space for the last century, are like a baby crying in a jungle full of tigers. Number 7, wormholes are mathematically possible and could connect infinite distances. In 1935, Albert Einstein and his colleague Nathan Rosen were exploring the mathematics of general relativity. They discovered a solution to the equations that described a bridge connecting two different points in spacetime. This theoretical structure came to be known as an Einstein-Rosen bridge, or more popularly, a wormhole. A wormhole is essentially a shortcut through spacetime. It is a tunnel with two mouths, which could be in the same universe or in two different universes. You could enter one mouth and instantly emerge from the other, even if the two mouths are billions of light years apart in normal space. It would be like folding a piece of paper in half and poking a pencil through it to connect two distant points. This sounds like the perfect tool for interstellar travel. However, the wormholes predicted by classical general relativity have some serious problems. First, they are incredibly unstable. They would collapse the instant they formed so quickly that not even a single photon would have time to pass through. Second, to hold a wormhole open, you would need a form of matter with negative energy or negative mass. This exotic matter has never been observed and might not exist. It would have bizarre properties like pushing instead of pulling with its gravity. But the idea has not been completely abandoned. Some physicists like Kip Thorne have done serious work on the properties of traversable wormholes. They have calculated the exact amount and properties of the exotic matter that would be needed to stabilize one. While we have no idea how to create such matter, some quantum effects like the Casimir effect do involve regions of negative energy density, though on a very tiny scale. If a technologically advanced civilization could somehow manufacture and control a sufficient amount of exotic matter, they could potentially create and maintain a wormhole. It would be the ultimate transportation network. You could step through a gateway in your living room and emerge on a planet in the Andromeda Galaxy. But it also opens up a host of paradoxes. Because a wormhole connects 2 points in spacetime, it could also be used to travel in time. By taking one mouth of a wormhole on a high-speed journey and then bringing it back, You could create a situation where the exit is in the past relative to the entrance. This would allow for time travel and all the logical problems that come with it, like the grandfather paradox. For now, wormholes remain firmly in the realm of theoretical physics, a mathematical possibility allowed by our best theory of gravity, but with no evidence that they exist in reality. Number 6. The entire universe might be a hologram. The holographic principle is one of the most bizarre and profound ideas to come out of theoretical physics in the last few decades. It suggests that our three-dimensional reality might be an illusion. It proposes that the universe is like a hologram, where the information for a 3D image is encoded on a 2D surface. The principle grew out of the study of black holes. Jacob Bekenstein and Stephen Hawking found that the maximum amount of information that can be contained within a region of space is proportional to the surface area of that region, not its volume. This was a shocking result. It is like saying the amount of data you can store on a hard drive depends on the area of its casing, not the number of platters inside. It suggested that information is fundamentally two-dimensional. This led Gerard Hooft and Leonard Susskind to propose that this might be true for the entire universe. The idea is that everything we experience in our three spatial dimensions, including ourselves, could be a projection of information stored on a distant, two-dimensional boundary at the edge of the universe. We perceive the world as 3D, just as we perceive the image from a hologram as 3D. But the fundamental reality, the source code of the universe, is written on a 2D surface. This is not just a philosophical idea, it has a concrete mathematical formulation in a branch of string theory called the ADS-CFT correspondence. This correspondence shows a mathematical equivalence between a theory of gravity in a certain kind of five-dimensional spacetime, the bulk, and a quantum field theory without gravity on its four-dimensional boundary, the hologram. This allows physicists to translate very difficult problems in gravity into simpler problems in quantum physics, and vice versa. It is a powerful mathematical tool, but does it mean our universe is literally a hologram? Some researchers have looked for evidence. A holographic universe would be grainy or pixelated at the smallest scales. A physicist named Craig Hogan at Fermilab designed an experiment called the holometer to search for this holographic noise, a fundamental jitter in spacetime itself. The experiment ran for several years, but did not find any evidence for this effect, at least down to the level of sensitivity it could achieve. The holographic principle remains a powerful theoretical concept that challenges our most basic intuitions about reality. It suggests that the space we live in might be an emergent property, a grand illusion projected from an infinitely distant flat screen. Number 5. The edge of the universe is a place in time, not space. The observable universe is about 93 billion light-years in diameter. This number is confusing because the universe is only 13.8 billion years old. How can it be so much larger? The reason is the expansion of space. When we look at a very distant galaxy, we are seeing light that has been traveling for billions of years. During the time that light was traveling towards us, the space between that galaxy and us has been stretching. So a galaxy whose light has taken 13 billion years to reach us is now much further away than 13 billion light years. The edge of the observable universe is defined by the cosmic particle horizon. This is the maximum distance from which light, emitted at the time of the Big Bang, could have traveled to reach us today. This distance is about 46.5 billion light years in every direction. So, what is beyond this edge? It is not a wall or a boundary. The best answer is simply more universe, more galaxies, more stars, more empty space, looking much the same as the universe inside our horizon. We just cannot see it. The reason we cannot see it is not a limit of space, but a limit of time. The light from those more distant regions has not had the 13.8 billion years necessary to reach us. An observer in a galaxy right at the edge of our observable universe would have their own observable universe, a sphere 93 billion light years across, centered on them. So they would be able to see parts of the universe that are invisible to us, and parts of our own observable universe would be invisible to them. This raises the question of how big the entire universe is. Is it just slightly larger than what we can see, or is it infinitely large? Our measurements of the curvature of space suggest that the universe is flat. A perfectly flat universe would be infinite in size. If this is the case, then our vast 93 billion light-year bubble of visibility is just an infinitesimally small patch of a truly infinite cosmos. This means that if you traveled far enough in any direction in this infinite space, you would eventually find another galaxy, another Earth, and another person identical to you. In an infinite universe, every possible arrangement of particles must repeat itself somewhere an infinite number of times. Number 4, reality only exists when we are looking at it. In the world of classical physics, objects have definite properties. A baseball has a specific position and a specific velocity, whether we are measuring it or not. The moon is still there even when no one is looking at it. This idea is called realism. But in the quantum world, things are not so simple. The dominant view, the Copenhagen interpretation, suggests that particles do not have definite properties until they are measured. Before a measurement, an electron exists in a superposition of all possible states. It is just a cloud of probability. The act of measurement itself is what forces the particle to choose a single state and become real. The physicist John Wheeler took this idea to its logical extreme with his concept of a participatory universe. He argued that we are not just passive observers of the universe, we are active participants in creating its reality. He proposed a thought experiment called the delayed choice experiment. It is a variation of the famous double slit experiment. In that experiment, a single photon seems to go through both of two slits at once, like a wave, creating an interference pattern. But if you place a detector at the slits to see which one it goes through, the interference pattern disappears and the photon acts like a particle going through only one slit. Wheeler's version adds a twist. You can decide whether to place the detectors at the slits after the photon has already passed through them. The results show that the photon's behavior seems to be determined by a choice we make in the future. If we choose to look for which path information, the photon will have behaved like a particle in the past. If we choose not to look, it will have behaved like a wave in the past. It is as if our observation now reaches back in time to determine the past reality. Wheeler argued this could apply to the cosmos as a whole. Billions of years ago, a photon left a distant quasar, traveled through space, its path bent by the gravity of an intervening galaxy, giving it two possible routes to Earth. For billions of years, it traveled as a wave of probability, taking both paths simultaneously. Then, today, an astronomer on Earth points a telescope and makes an observation. That act of observation in the present forces the photon to have chosen a single path billions of years ago. In this view, the universe is a vast, interconnected quantum system. The past is not fixed. It is an unregistered history until it is brought into reality by an act of observation in the present. Without conscious observers, or at least some form of measurement, the universe would remain a ghostly sea of infinite possibilities, with no solid reality at all. Number 3, there is a wall of fire at the edge of a black hole. For a long time, the picture of falling into a black hole was relatively gentle, at least at first. According to general relativity, if you were falling into a supermassive black hole, you would cross the event horizon without noticing anything special. The point of no return would be an invisible line in space. You would only be torn apart by tidal forces, or spaghettification much later as you approach the singularity. This view was challenged in 2012 by a group of physicists, including Joseph Polchinski. They identified a deep contradiction between 3 fundamental principles of physics when applied to black holes. The first is Einstein's equivalence principle, which states that a freely falling observer should experience the normal laws of physics and not feel the effects of gravity. This is why astronauts in orbit feel weightless. It implies that the event horizon should be an unremarkable place. The second principle is that information is never lost, the core idea behind the solution to the information paradox. The third is the principle of locality, which says that events can only be influenced by their immediate surroundings. Polchinski and his colleagues showed that you cannot have all three of these principles be true at the same time for a black hole. You have to give one up. They argued that the one to go must be the equivalence principle. This leads to a dramatic new picture. Instead of being an empty, unremarkable place, the event horizon is a firewall, a high-energy wall of fire that would instantly incinerate anything that tried to cross it. The firewall is created by the entanglement of quantum particles. Hawking radiation is caused by pairs of entangled particles being created at the event horizon, with one falling in and one escaping. For information to be preserved, the outgoing Hawking particle must be entangled with all the radiation that has previously left the black hole. But a quantum mechanics rule called monogamy of entanglement says that a particle can only be fully entangled with one other partner. It cannot be entangled with both the particle that fell in and all the old radiation. To resolve this, the entanglement between the infalling and outgoing particles must be violently broken. The energy released by breaking this bond is what creates the wall of fire at the event horizon. This idea is extremely controversial. If the firewall exists, it would be a radical departure from Einstein's theory of gravity. Many physicists are working on alternative solutions to the paradox that do not require such a dramatic structure. But the firewall paradox highlights how our two best theories of the universe, general relativity and quantum mechanics, are still in deep conflict when it comes to the infinite extremes of a black hole. Number 2, the universe could be one bubble in an infinite frothing sea. The theory of cosmic inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid exponential expansion. It grew from smaller than an atom to larger than a galaxy in a tiny fraction of a second. Inflation does an excellent job of explaining many observed features of our universe, like why it is so flat and uniform on large scales. But a consequence of many inflation models is that inflation might not stop everywhere at the same time. The process that drives inflation is a quantum field called the inflaton field. Like all quantum fields, it is subject to random fluctuation. So, while inflation might have stopped in our region of space 13.8 billion years ago, allowing our universe to form, it is likely still raging on in other regions far beyond our cosmic horizon. This is the theory of eternal inflation. The idea is that the wider metaverse is an eternally expanding sea of inflating space. Within this sea, quantum fluctuations will randomly cause small pockets of space to stop inflating and decay into a stable state. Each of these pockets becomes a new bubble universe with its own Big Bang. Our entire observable universe would be just one of these bubbles in an infinite frothing ocean of other bubbles. This picture, developed by physicists like Alan Guth, Andre Linde, and Alexander Vilenkin, creates an infinite multiverse. New bubble universes are constantly being born from the inflating sea, each one potentially infinite in size itself. This multiverse could be incredibly diverse. The laws of physics might be different in each bubble. The process of inflation and decay could randomly set the values of the fundamental constants, like the strength of gravity or the mass of the electron. This provides a natural explanation for the fine-tuning problem. With an infinite number of bubble universes, each with different physical laws, it is inevitable that some of them will have the right conditions for life to exist. We simply find ourselves in one of the bubbles where we could evolve. The theory of eternal inflation is not directly testable. We can never hope to see another bubble universe, as the inflating space between them is expanding far too fast for any signal to cross. But it is a natural and, for many cosmologists, a compelling consequence of our best theory for the origin of our own universe. It suggests our existence is just one of an infinite number of cosmic experiments. Number 1. The dark forest is quiet for a reason. The numbers suggest our galaxy should be filled with civilizations. There are billions of potentially habitable planets. Life has had billions of years to evolve. Even if only a tiny fraction of those planets developed intelligent life, and a tiny fraction of those developed interstellar travel, the galaxy should have been colonized many times over by now. Yet we see nothing. No probes, no signals, no giant alien structures, just silence. The dark forest hypothesis offers a chilling explanation for this silence. It starts with 2 axioms. First, the primary goal of any civilization is survival. Second, a civilization can never be certain of the intentions of another civilization, especially one that is technologically superior. Now, consider a new civilization that announces its presence to the galaxy, perhaps by sending out a powerful radio message. An older, more advanced civilization detects this message. What should it do? It cannot be sure if the new civilization is peaceful or hostile. It cannot be sure that if it reveals its own existence, the newcomers will not one day become a threat. The distances between stars are vast, making communication slow and difficult. Building trust is almost impossible. Given the existential risk, the most logical, safest course of action for the older civilization is to eliminate the potential threat before it has a chance to develop. It is a cosmic game theory problem where the penalty for being wrong is extinction. The result is that every civilization in the galaxy learns to do 2 things: hide and listen. They stay as quiet as possible to avoid being detected by potential predators, and they listen for any other civilization foolish enough to make a noise. If they hear one, they destroy it, not out of malice, but out of fear. The universe is a dark forest. Every civilization is a hidden hunter. The first one to light a fire gives away their position and is silently eliminated by another hunter they never even saw. This hypothesis from Liu Cixin's novel The Dark Forest turns the Fermi paradox on its head. The silence is not evidence of absence, it is evidence of presence. The reason the sky is quiet is because the survivors are the ones who have learned to be quiet. It implies that our efforts to send messages into space, like the Arecibo message, are incredibly naive and dangerous. So, we are shouting in a jungle that we do not understand, and we have no idea who or what might be listening. The silence is not empty, it is watchful.